Plates, however, work on a different time scale. So then the wobble associated with that is true polar wander. And it is a bit of a complicated matter, I'll admit, but effectively, Earth tries to rebalance things. So if you've got slabs sinking here with these blue blobs going down, and you have mantle plumes rising, which are these orange blobs going up, Earth will try to adjust that and have the heavier slabs adjusting to closer to the spin axis. I'm not sure if this is entirely correct, but it's basically in the end, the Earth will rotate relatively to the magnetic field, which is determined in the outer core. And this is true polar wander. So the mantle and the crust rotate relatively to Earth's spin axis as determined by the core and the outer core. So what is known about true polar wander? There's a few models where people have used this to explain when all the plates are moving a particular direction, which is odd, right? So you would expect that all plates would move certain ways, but if they're all moving at the same time in the same direction, it is as a result that really the whole mantle and crust are moving relatively to the magnetic field. So there's various models trying to quantify this from Trond Torsvik, who I've known from spending some time in Norway, an expert in these matters. He's tried to quantify that. There's been a few follow-up studies as well. Overall, you get to rotation of maybe 1 degree per million years. So over a period of 10 million years, for example, you could have had 10 degrees that the whole Earth has moved. I wish, however, that there was more consensus on that. As I said, various studies have tried to quantify it, and every time they have a peak of true polar wander at a different time. So at the moment, I would say the academia still haven't figured this out yet. The data is simply not sufficient yet to quantify true polar wander. And any kind of peaks could very well still be artifacts of the data at the moment. Okay, so what would be the causes of true polar wander? Well, one key reason is as said, these sinking slabs and these rising plumes, so these density anomalies within the mantle. So, and that's just then effectively the offset of the center of mass here, where Bob prefers to have the core displaced from the rotation axis, but I would say there are density anomalies from crust to the mantle to the core, so it could be at any given depth here. So we are aware that Earth is not perfectly symmetric. We see it in the geoid, where if you would have sea level following across the Earth, it won't actually be at the same distance compared to the center of the Earth, and this is the result of the density anomalies. We also have in shorter wavelengths various density anomalies. So, for example, in Bouguer gravity or isostatic anomaly as such measured across the Earth, you can see the effect of ice caps. You can see the effect of mountain ranges, of trenches, and anything else that disturbs the homogeneous density field as such. So the geoid, just to give you an idea, it's very much a potato-shaped Earth. If you look at the Earth from a gravity point of view, and as said, this is basically if you would follow if you would go with a boat across the Earth, and you would be able to measure the distance to the center of the Earth, you will be going up and down as you travel across the oceans. Across the Earth, and that's as a result because of the different densities deeper in the Earth. So how can we look deeper into the Earth? We use computed tomography. which is being applied in hospitals as well. So it's so-called CT scans, for example, to look into someone's brain or other parts of the body. In the Earth, we use earthquake waves, where basically earthquake waves traverse through the Earth. And as long as you've got enough earthquakes and receivers at either end of the Earth, you can make an image of which areas are relatively fast versus relatively slow for waves to travel through. And then the faster regions are typically colder, denser material, which are associated with these sinking slabs, which you can see one here, for example, sinking down at the west coast of South America. So if you take a cross section, just as an example here, again from the western part of South America to all the way to Africa, you can see this sinking slab as a result of subduction here at the Nazca Trench, and that slab is sinking. Whereas the counterflow are mantle plumes, which in this case it appears, you see this in this red anomaly, and it's appearing more or less at where the African Rift Valley is in East Africa. Another thing what I want to point out is you see this large red blob here, and this is the so-called African Large Low Shear Wave Velocity Province, which is a structure that has been described in seismology, but people don't fully understand yet what it is. So just to complete this here, the LLSVP, in short, is a deep structure there where the jury is out how long it's been there. What we do know, there's the African LLSVP, there's also one on the other side, in the Pacific side. So as Liz was showing, Bob's theory is that all the plates are drifting away from Africa, and that is true. And they're drifting away from this LLSVP, which you can see in the geoid here in the reddish colors. Sorry, in the LLSVP in the reddish colors, which also corresponds with the higher geoid. There's a similar feature also on the Pacific side. So maybe in the past, the Pacific plate originated there and started spreading from that location. So it's not only continental plates that might be affected by the LLSVP. It might also be oceanic plates and at the Pacific side. Now, what I want to point out is Earth is not alone in these features. Oh yeah, there's also a link with volcanism, by the way. And we see the same thing in Mars. So I already mentioned the geoid. In Mars, it's called the areoid. And again, you've got two highs, two areoid highs, which also have a link with volcanism. And I believe Olympus Mons is probably one of the bigger ones here. And so it's interesting, right? So you've got two planets that have offset center of masses that are detectable, at least from surface. So in the Earth, there is debate, however, how long they've been there. There's one theory is basically they must have been there for at least 500 million years and must be stable, rigid, and denser. Another theory is basically they will move aside, it's more flexible, and the position of these are just simply dictated by the absence of subduction since at least Pangea times. And academia haven't figured this out yet. Well, it's either one of the two, or maybe a combination of two, who knows. I just want to jump to the moon briefly. The moon also has an offset center of mass. You've got the mares, which are the darker patches of the Earth that we always see. That's the near side of the moon. So that's also where it's the heavier side of the moon is towards us. Whereas the lighter side of the moon, which are the highlands, which is a lighter type of rock, it's all basalt in some way or form, but it's a lighter type. That's the far side of the moon, the side of the moon that we don't see from Earth. So in a way, the fact that Bob postulated this offset center of mass, I was actually very pleased that other planets, Mars, and also the Moon have that. Now, is the offset center of mass caused by the core being offset, in addition to all the other effects in the mantle and the crust? Well, maybe. This is a very interesting recent article from Paula Koelemeijer. I think she was in Oxford. She was comparing the different tomographic models, and she calculated basically that the core mantle boundary, or CMB here, does vary between these models, and varies between 1 kilometer to up to 10 kilometer in one set, and in somewhat higher resolution, 1 to maybe 15 kilometer difference between the peaks and the troughs of the core going up and down with respect to the mantle. The downside is that all these models are very different, and I've stared very long at these images, but I couldn't find any consistency between them. So yes, the core is probably not perfectly round. It is somewhat offset, maybe from the spin axis, but where it is exactly, science can't tell at the moment. Then, going even deeper, there's even more anomalies within the core. There's also the inner core here, which is still crystallizing. So the inner core is solid, the outer core is liquid. The inner core is still growing. And there's an asymmetry to that, where is on the one side flow is going downwards, material is accreting, and on the eastern side flow is going upward, and there's a sort of enrichment of lighter elements on one side. So, and obviously that would have to result in some kind of density difference. So again, some evidence of an offset center of mass here. And even deeper down, there's more. Within the inner core, again, is not homogeneous. Also there's some heterogeneity. So that's all what I couldn't summarize so far. So to summarize my investigation, so Bob is right. The Earth is unbalanced due to density, heterogeneity in core, mantle, and crust. So you can summarize this as was one single point of an offset center of mass, but the reality is it's accumulation of all these different kind of anomalies together. There's unfortunately just limited consensus on the severity on all of these, and especially the deeper you go. And then how does it relate to Earth's wobbles? Well, eccentricity, probably not. That's very much outside of the Earth. Precession, obliquity, maybe some effect of the mantle in there, which is not quantified by academia. And I said there might actually be something to be said that the ice caps are actually self-enforcing and destructing each other because of creating some kind of two-polar wonder. And then for the multi-million-year two-polar wonder, yes, this might be due to long-term offset center of mass, which I said this can be due to heterogeneity within core, mantle, and crust. So all in all, I would say Bob's research has been very inspiring and has provided much food for thought, at least for myself. And if anything is clear, is that more research is needed, especially as you go deeper down in the Earth. And I'll leave it at that.
Thank you very much, Douwe.